Hello, statistics and precalculus. I hope you have your big blue book open to page number 9. We're looking at logarithmic functions here. Going to graph a logarithmic function. We have the graph of the log base 2 of x here, but everything we're doing here applies to a base, any base, including base e, the natural logarithm. So for any of these functions, the domain is x greater than 0. X has to be a positive number. You cannot take the logarithm of a negative number. You cannot take the logarithm of 0. So your domain is going to be x greater than 0. You can also write that as the interval from 0 to infinity, not including 0, so an open parentheses at 0. The range, however, is all real numbers. So any real number, negative infinity to infinity is your domain, is the range. You notice that that's very similar to the domain and range of the exponential function, only flipped, because the logarithmic function is the inverse of the exponential function. So x becomes y becomes x, domain becomes range, and range becomes domain. The y-intercept of 1, 0 on the y-intercept of 0, 1 on an exponential function becomes an x-intercept of 1, 0 on a logarithmic function, and there is no y-intercept. The asymptote of y equals 0 on an exponential function becomes an asymptote of x equals 0 on the logarithmic function. That's also known as the y-axis. X equals 0. The y-axis is a line that this function will approach but will never reach. It'll keep getting closer as you move on down. The key points here, the same as before. 1, 0 is a key point on any graph. Also the base and 1, and then the base squared. And 2. So because the logarithm is asking what's the power, whatever your exponent is becomes the y-coordinate. There is no symmetry here, although it is a reflection over the line y equals x of the exponential function. But the logarithmic function by itself does not have any symmetry. Moving on. It is, however, continuous on its entire domain. It is continuous on the domain from 0 to infinity. The end behavior on the right end, as you expect, as x approaches infinity, y also approaches infinity, but it's interesting, it approaches infinity very slowly. If you remember the exponential function, it approached infinity very quickly, and a logarithmic function approaches very slowly. But the end behavior on the other side is a little tricky because x never gets less than 0, never even reaches 0. So the left end, x is approaching 0. It's not approaching negative infinity. So the left end is at 0, and here y approaches negative infinity. As you can see from the graph, it's approaching negative infinity down here. There are no maximum and minimum points. It is increasing on the entire domain. So increasing everywhere from 0 to infinity. The whole shebang is increasing, and it increases quickly at the beginning, but then more and more slowly, sort of the opposite of the exponential. No special alternative forms, although it is the inverse of the exponential, as you know, and applications for solving exponential functions. It is definitely a logarithmic function is definitely the tool you want, and there are some things that in the world that behave logarithmically, at least for a time, things that grow quickly at first and then slow down. So for instance, how tall people are. When you're a baby, you grow very quickly at first, as you become a teenager, you're growing more and more slowly, and probably most of you at 16 and 17 years old are not going to grow much taller than you are right now. You're growing very slowly. So there we go. That's a possible exponential application. Logarithmic application. Enjoy. Have a good day.